Hey everyone. Okay, if you're staring down a computer vision midterm right now and feeling that familiar wave of panic because you maybe missed a few lectures, just take a deep breath. You are in the exact right place. Consider this explainer your ultimate exam survival guide for Unit 1 and Unit 2. I'm going to act as your personal professor today, and together we're going to break down exactly how machines learn to see, from the absolute basic pixels all the way up to how a self-driving car spots a pedestrian. So get comfortable because we're going to make this efficient, super focused, and incredibly effective. Let's do this. Here is our roadmap for today's review. We'll hit the basics of computer vision, pixels, formats and colors, edges, blobs and corners, descriptors and feature matching, and finally, we'll wrap up with a rapid exam revision to really lock in those easy points. All right, Section 1, Basics of Computer Vision. Let's define what it actually means for a machine to see. Now, I can practically guarantee this comparison is going to show up on your exam. It's an absolute classic. Image processing is all about the prep work. If you're resizing an image, applying a blur, or increasing the contrast, you are doing image processing. The output is just another, maybe slightly better, image. Computer vision, on the other hand, is the brain making a decision. It takes that image and extracts actual meaning. If the system says, hey, this is a 90% match for a dog, or it automatically applies the brakes on a car, that is computer vision. In short, image processing enhances, computer vision interprets. So when we look at how modern AI processes these images, standard artificial neural networks, or ANNs, they kind of try to look at the entire photo all at once. They basically stretch 1,000,000 pixels into a single massive line of data. And the result? Well, they completely lose the map of where things are. It's like the network forgets that a nose is supposed to be below the eyes. But convolutional neural networks, or CNNs, do this entirely differently. They read the image line by line using small, typically 3 by 3 patches, just sliding over the image. This preserves the map of the visual features. That's why ANNs are great for, say, basic spreadsheet data. But CNNs, they're the absolute standard for face filters and real computer vision. Moving on to Section 2, Pixels, Formats, and Colors. Let's trace how light goes from the real world, through the lens, and onto the camera's sensor. Listen closely here, because this is absolute multiple choice gold. When a sensor captures light, it has to convert a continuous, real-world scene into a digital file that the computer can actually read. It does this in 2 very specific steps, sampling and quantization. Sampling answers the question, where? It takes the continuous physical space and chops it up into a discrete grid of pixels. Quantization, on the flip side, answers the question, value. It looks at the brightness of the light in that pixel and assigns it a discrete number. In a standard 8-bit grayscale image, because 2 to the power of 8 equals 256, that value is going to be a number from 0, which is pure black, all the way to 255, which is pure white. Now, when we bring color into the mix, things get a little bit more complex. You really need to memorize these models for your short answer questions. The rule of thumb here is super simple. RGB stands for red, green, blue. It's an additive model used for light on digital screens. CMYK stands for cyan, magenta, yellow, and key, which just means black. That's a subtractive model used for ink on paper printers. And if your exam happens to ask about YIQ, just remember it's the standard used for analog television broadcasting. But the most interesting one for computer vision is actually HSV, which stands for hue, saturation, and value. Because HSV separates the actual color, the hue, from the brightness, the value, it makes it incredibly robust for algorithms that are trying to track a specific color under changing lighting conditions. Okay, Section 3, Edges, Blobs, and Corners. How exactly does a computer search through a giant grid of numbers to find interesting landmarks? Instead of trying to blindly match 1,000,000 pixels, computer vision looks for specific, robust landmarks called features. Let's use a quick, intuitive analogy for the 3 main types. An edge is a place where brightness changes sharply in one direction. It's basically like tracing the silhouette or boundary of a shape with your finger. A blob is a distinctive circular region that's distinctly brighter or darker than its surroundings. Think of it like spotting a coffee stain on a shirt. And a corner is a point where the intensity changes sharply in all directions. Imagine looking at a single black square on a chessboard. No matter which way you slide your view, the pattern changes completely. If you get a process-based long answer question on edge detection, Canny is the absolute gold standard, and you must list these exact 4 steps in order. First, you smooth the image with a Gaussian filter.
to get rid of noisy pixels. Second, you compute the gradient using an operator like Sobel, Pruitt, Roberts, or Laplacian to find where the intensity actually changes. Third, you apply non-maximum suppression, which is really just a fancy way of saying you thin out the edges so they're only exactly 1 pixel wide. And finally, you use hysteresis thresholding to link strong edges together and discard the weak, disconnected ones. Seriously, memorize those 4 steps. Now, when looking at the Harris corner detector, don't panic. You likely won't need to derive this scary-looking math from scratch. You just need to know how to interpret the final score, which is R. The math builds a matrix of gradients around a point. If the final calculation of R is a large positive number, boom, you found a corner. If R is a large negative number, it's just an edge. And if the absolute value of R is very small, you're just looking at a flat, totally featureless region. Oh, and a quick exam tip, if they ask about the Sheet-Tomasi detector, just know it's a slight mathematical tweak to this Harris formula that often computes better, more stable corners. Moving right along to Section 4, descriptors and feature matching. Now that we found these features, we need to give them unique fingerprints. Please do not fall for this classic trap on the exam. Do not confuse these two terms. Feature detection is simply finding where the feature is. It just gives you the X and Y coordinates. It basically says, hey, there is a corner at pixel 120/85. Feature description, on the other hand, is explaining what that feature looks like. It provides a mathematical array of numbers that describes the visual neighborhood around that point, acting as a completely unique ID tag. But think about this for a second. What happens if an object is closer to the camera in the second photo? A corner might suddenly look like a soft edge. This problem is solved by scale space. Intuitively, building a scale space means taking an image and applying increasing levels of Gaussian blur, often using methods like the Laplacian of Gaussian, or LOG. It's kind of like zooming out on a photo until the small details just vanish and only the big, defining shapes survive. This is crucial because it allows the computer to find the characteristic scale of an object, meaning it can confidently match a feature whether the camera is 2 feet away or 20 feet away. And that brings us to the absolute king of descriptors, SIFT, or the Scale Invariant Feature Transform. This is the ultimate, robust fingerprinting tool. It uses that difference of Gaussian scale space we just talked about to find key points, removes the weak ones, assigns them a dominant gradient orientation so it actually survives rotation, and finally generates 128-number descriptive vector. SIFT literally doesn't care if your image is zoomed in, rotated, or has slightly different lighting. It's going to find the match. But, SIFT has a bit of a problem. That 128-dimensional math is computationally heavy and it is slow. Enter its faster sibling, SURF, which stands for Speeded Up Robust Features. This is an extremely common exam comparison, so jot this down. While SIFT uses the difference of Gaussians, SURF uses the Hessian matrix and approximates the math with quick box filters and integral images. The result? SURF gives you a 64-dimensional descriptor instead. It's slightly less robust than SIFT, sure, but it is significantly faster, which makes it perfect for real-time tracking in robotics or mobile apps. Now, what if we don't want to match tiny specific points, but instead describe whole regions? For this, you need to know HOG and LBP. HOG stands for Histogram of Oriented Gradients. It describes the shape and silhouette of an object by looking at the direction. The local binary patterns is all about feeling the texture of a surface. It looks at a pixel, compares it to its 8 immediate neighbors, and generates a binary code to describe if the texture is rough, smooth, or patterned. It's heavily used in things like facial recognition. All right, Section 5, Rapid Exam Revision. Take a deep breath. Let's lock in everything you've learned today. Get ready to screenshot, because this right here is your ultimate cheat sheet. When you see the word sampling, I want you to immediately think where on the grid. Quantization, that is the value from 0 to 255. An edge is a boundary. A corner is a distinctive point that changes in all directions. A blob is a distinct region or stain. Link these words in your head right now. Keeping that momentum going, feature detection gives you the where coordinates. Feature description gives you the mathematical what. And if they ask about the ORB algorithm, just remember it's a fusion. It uses the fast detector to find the points and the brief descriptor to mathematically describe them. Finally, let's nail down those format basics. JPEG is lossy, meaning it deletes data that saves space. PNG is lossless. It keeps absolutely everything sharp and supports transparent backgrounds. RGB is adding light for digital screens. CMYK is subtracting light using ink for printing. Lock these absolute basics in and you are going to save precious minutes on your exam for sure. And that brings us to the end. Let's test your new knowledge with one final thought before we wrap up. If you were programming a self-driving car and needed an algorithm specifically designed to recognize the shape and outline of a pedestrian walking into the street, which of the extractors we covered would you choose? Think about it. If you said HOG, the histogram of oriented gradients, you are absolutely right. You've got this. Best of luck on your midterm. Now go crush it.